will be delivered by Jack Steinhauser. The title of the presentation is AI-driven data centers and demand impact: a day on the ERCOT grid. And so it has elements of many issues that are very relevant to what's going on today as far as data centers are concerned. Let me read the background for Jack. He's a dynamic energy industry leader with over 40 years of experience leading growth, innovation, and capital formation across traditional and renewable sectors. As a proven CEO and advisor, Jack excels in guiding companies through the low carbon energy transition from oil and gas exploration to renewable power generation, including solar plus battery systems, waste to energy systems, hydrogen fueling infrastructure, and AI driven technologies. His career highlights include raising more than $270 million in project financing, divesting 29 million in assets, and managing companies in crisis scenarios. His executive tenure spans three publicly traded Canadian and oil and gas firms, where he orchestrated over 50 exploration and development projects across North and South America, as well as Eastern Europe. As president and CEO of Sharon Energy, he assembled drilling ventures and secured 25 million in joint venture funding from 176 wells across 9 U.S. states. He later led Gold Point Energy Corporation and Wind River Energy Corporation, raising 14 million and 10.5 million, respectively, Canadian dollars, while navigating public listings on the Toronto Venture Exchange and executing business plans which included projects in South America and East Europe. His expertise in corporate finance, project management, and crisis leadership, backed by a bachelor's degree in economics and master's degree in international management, enables him to forge high-performance teams and navigate complex deals in a legacy and emerging landscape. A sought-after communicator, he builds enduring stakeholder relationships to unlock value and mitigate risks. So, without further ado, let me have Jack take over the floor.
All
Jack?
right. Well, thank you very much, Rudy. It's a pleasure to be here. Good morning, everybody. My name is Jack Steinhauser. I'm an energy executive with over 40 years experience in both the oil and gas industry and electrical generation using modern renewable technology. Before I begin the presentation, I want to extend my sincere thanks to Rudy Shanker. He invited me to speak today and has been very encouraging. I also appreciate everything that Susan Karanek has done to handle all the logistical details for this presentation. So my presentation today is titled AI-Driven Data Center Demand Impact, a Day on the ERCOT Grid. And it seeks to explore the biggest phenomenon going on in the business world today, which is the build out of trillions of dollars worth of data centers and the power generation facilities needed to power those facilities. But first, we're going to step back to take a wider view of what's really going on. We'll start by capturing the impact that the use of hydrocarbons for energy pioneered in the Industrial Revolution and continued through the digital revolution has had on the quality of life for humans. Then we introduce the topic of man-made climate change and the need to moderate that impact by evolving to an energy system that is less carbon intensive. That energy transition is underway, and the question for humanity is whether it will occur fast enough to avoid the worst outcomes that have been predicted. I will then take a look at the evolving power generation system in the United States and take a quick peek at what is happening in China for comparison. Renewable power sources like solar and wind are intermittent. That means that if we are going to use them to provide substantial amounts of electricity, we need to shift the power from when it's generated to when it is used. And that is where battery energy storage systems come in for short-term applications, and other storage technologies can work over longer time periods. The AI revolution is the most profound change in technology and its impact on humankind to ever occur. It will change everyone's life in profound ways. Some impacts will be beneficial. Others will cause negative impacts like job losses. There are those who believe that AI could lead to more traumatic impacts on humanity, and others who believe that the changes will be hugely beneficial. But one thing is for certain, AI will need gobs of electric power. The build-out of the electrical generation infrastructure to support the power needs of AI is one of the greatest infrastructure projects ever undertaken. Trillions of dollars will be spent, millions of jobs will be created, and I hope that everyone listening today has the opportunity to advance their career, and I mean the students in this case, by being a participant in this once in a generation electronic gold rush. To better understand where the ERCOT grid fits into the overall picture, we will look at the organizations that control the electrical generation, transmission, and distribution infrastructure that makes up the North American grid. We will also take a look at some of the technical basics of the grid, such as the use of AC versus DC electric current for specific applications, and that will bring us to the Electrical Reliability Council of Texas, which is an independent system operator. We will look at who owns ERCOT, how it works, and what it does. We'll take a look at a single day of operations on the ERCOT grid to see how it handles a variety of electrical generation sources, which include nuclear, coal, natural gas, solar, and wind, complemented by battery storage to seamlessly deliver the power Texans need every day. Data center developers are at the eye of the hurricane that is the massive data center buildout. They face a series of challenges and have limited choices for making everything work. One of these choices is to use behind the meter generation facilities. And this seems to be the major trend. So we're going to take a look at how this works by looking at an example of a facility that is insanely large and combines natural gas from the Permian Basin, solar, and batteries to provide data for a massive data center facility in West Texas. All of the students that are attending today will have access to a PDF copy of this presentation. So there may be a lot of notes that you'd like to take, but realize that you'll be able to get the whole presentation. And I believe the presentation is going to be recorded and posted to YouTube. So let's get started. What I'm going to do now is I'm going to share the presentation itself.
Real quick, can I interrupt, Jack?
Yeah.
Adam, did you have your hand up? You had a question?
I was meaning to ask if he was sharing or trying to share slides.
Okay. Yeah, he's not there. He's not sharing yet, but yes, thank
Okay.
you. There we go.
Yeah. Okay. So does everybody see that?
Yep.
Yeah.
Okay. Thanks for the question, Adam. All right. So for today, we're going to take a look at the importance of energy for humanity, greenhouse gases and global warming, the U.S. energy system, the energy transition, the role of battery energy storage systems, the AI revolution and power demand, the North American and USA power grid. We'll take a look at ERCOT, the challenges that data center developers face, and one of the solutions, which is the behind the meter type of facilities. Let's start out with energy use and quality of life. So the harnessing and utilization of energy has had a major impact on every aspect of human existence over the past 2 centuries. Those 2 centuries have coincided with the use of coal, then oil and gas that powered the Industrial Revolution. And by the way, Pennsylvania has been ground zero for a lot of this stuff. Pennsylvania has been the center for the development of the oil industry and also for much of the coal industry. And whether or not the mines were located in Pennsylvania, the technology was certainly developed at places like Lehigh. And then subsequent to using all the power that could be harnessed by steam and from oil and gas, we've seen the widespread use of electricity powered by hydrocarbons to power the information age. Before the Industrial Revolution, there were roughly 1 billion people on the planet Earth. Now there's 8. And even though there's many, many more people, today people enjoy a quality of life that is much better than they have in the past, better than the royalty of past ages. And life expectancy, which is a good proxy for that, has increased by 2 to 3 times. This graph shows the use that started back in the dawn of the Industrial Revolution back in the 19th century and how that expanded gradually until about the time of World War II. And subsequent to World War II, in the last 80 years, we've seen a dramatic expansion of all of these sources of energy that include coal, oil, natural gas, hydro, and nuclear. And at the same time, we can see that the life expectancy around the world has grown dramatically. Used to be that people rarely live past 30 years old. And today, basically starting at the first part of the 20th century, we saw that increase. And today we're basically up around 70 to 80 years is an average life expectancy. But there's a hidden cost to all of these benefits, and that has been that the extraction and burning of fossil fuels has increased the level of greenhouse gases. So during the time frame that we're looking at, carbon dioxide is up by 50%, and methane, which is a very powerful greenhouse gas, is up by 162%. And as a result of that, we've seen the average temperature around the globe increase by 1.3 degrees centigrade. And in some places, for example, in the Arctic regions, the increase in temperature has been much more substantial. And we are now seeing everywhere around the globe the result of the increase of that temperature. And we're seeing, for example, more severe storms, increased rainfall, rising sea levels, which are up by 5 to 8 inches around the world, and also the impact on agriculture. I had an experience 2 years ago in April. I was in Dubai. I was there on business, and they had an incredible rainstorm. And for a place that gets an average rainfall of about 2 to 3 inches of rain per year, they had about 10 inches of rain in a single day. So it was amazing to watch, and it is happening all around the globe. We see stories of flooding in, Europe and Asia, the US, South America, everywhere around the globe, these events are taking place. This is a log graph, and I'm assuming that everybody's going to get that idea. Actually, it's a semi-log because this scale, which is time, goes back to essentially the beginning of life on Earth, so 400 million years ago, and goes to the present. And the first gradient here is 1,000 years. So this period of time is 1,000 years, then 10, 100,000, a million years, and so on and so forth. And then this axis here shows the rise in the CO2 parts per million. And at times in ancient geologic history, we could see that the CO2 levels were very, very high. And we could see that they decreased. And then after a period of instability, during the last 10,000 years, which coincides with the Neolithic to modern man period, the level of CO2 has been very, very stable. Okay, so during that time, we saw the rise of civilization. Before Neolithic, you had Paleolithic. Those are stone tools. Neolithic was the rise of modern agriculture, metal tools, societal construction, all the things that are attributes of modern society. And you can see that this graph, which goes along very stable here, started to go up quite dramatically in the latter part of the 20th century, and we are now at 426 parts per million of CO2. And these various lines here are projections of where it could go depending on choices that humanity makes. Basically, how many hydrocarbons and how much CO2 do we release into the atmosphere will result in one of these future scenarios. Some of them are catastrophic. Some of them imply large-scale extinction events. And so really the job that we have as a species is to try and keep this as low as possible, but maintain all the benefits that energy gives us. Here's another way of looking at that same data. This is a graph that shows the rise in temperature that's occurred really since about the 1960s to the present day. So we're basically bumping up against the Paris target of 1.5 degrees centigrade of total rise. And then this graph basically is every year is plotted across, and you can see, the temperature from the coldest part of the year through the hottest part of the year to the end of the year. And you can definitely see there's a shift to the right here. The last 5 years have been some of the hottest on record. If we look at the US energy system, we can see that there's a reliance on fossil fuels. That's been the primary source of energy. And on this graph, from starting from the top here, you can see natural gas, crude oil. The next line down is the coal. And then we've got renewables and liquids, and we've got nuclear in there as well. And notice that what happened to oil and gas back starting about the late aughts, 2008, we started to see an increase in both. And this is caused by the fracking revolution, which took place. I'll explain that in a minute, but I want you to note that the rise in natural gas production, which went from about 20 quadrillion BTUs up to its present level, which is twice that number in about 15 years, basically also coincides with the decrease in the use of coal. So coal went from about 25 quads and it's now down to 10. And that's important because coal, of all the fossil fuel choices, has the most cost in terms of CO2 emitted per unit of energy created. So fracking or fracture stimulation is the revolution that created this bounty of oil and gas being produced in the United States. And it's important to realize that the U.S. does not have the biggest oil and gas reserves in the world. It's actually way behind some other countries, including Venezuela and Saudi Arabia and many of the countries in the Persian Gulf. But what we have is a very efficient oil industry, and they've used this technique to accelerate production from low quality reservoirs. So I've been in the oil business since the early 80s. During that time, most of the work I did was focused on the search for conventional oil and gas reservoirs. And what fracking has done is it's opened up very low quality reservoirs. And the way that that works is that if a reservoir, and let's just use this and just say that that is 50 feet thick, okay? So if you drill a vertical hole, you get 50 foot of exposure to the reservoir. But if you go down and drill out a horizontal hole, you can go out a mile, 2 miles, 3 miles, 4 miles, and therefore you get all of that reservoir being exposed to the wellbore. And by uh, using hydraulic fracturing, so you're using fluids and sometimes the addition of sand to literally fracture open the formation and release all of the oil and gas that's in there to come back up the wellbore and go into your reservoir or your tanks here. And the effect of this is that these wells basically produce generally a lot more oil and gas than a typical vertical hole, and they do it at higher rates initially. And since they're drilled into a known reservoir, they're almost always successful. Now, they're very expensive. They can cost, 5 or 10 times the cost of a vertical well. But if you get a well every time, then it's a great thing. And you can see the impact on the production. Now, during the same time that that fracking revolution has been taking place, we've seen an energy transition in motion. And that energy transition is characterized by the rise of renewable power, by the rise of storage and energy efficiency and electrification. Meanwhile, we've seen oil go down slightly, and this is a global picture in terms of investment, but oil has gone down slightly, natural gas has gone down considerably, and coal has gone down. So we're seeing that these other forms of energy that do not contribute the large volume of carbon, CO2 and methane and other greenhouse gases are really starting to come to the fore. This is another way of looking at that production in the US. So at the bottom of this graph here, you've got coal, then you've got natural gas, nuclear, renewables. Oh, this is petroleum here. This is renewables. So basically, these middle segments are all hydrocarbons. That's hydrocarbons. So all of this is hydrocarbons. And then on the top, you've got renewables. And I want you to look at this table here because this is the net additions to electrical generation capacity that occurred in 2025 in the United States, of which 72% was solar, 17% was wind. Combine those two, you've got 89% of the additions to the US electric grid last year were from renewable sources. Natural gas was only 4.4 gigawatts, although that's about to change in a big way. Nuclear was very small, and the other sources are pretty much insignificant. And at the same time, there's been a tremendous addition of battery storage. And we'll learn a little bit later in the presentation why battery storage is so important. But that's a major addition to the grid is that storage figure. Now, this is a concept that's been advanced by a group called Ember Energy. They call it the Electrotech revolution. It's a good way to understand what's actually happening in the energy transition. And they basically start out with three reinforcing shifts that are occurring in the energy infrastructure. So first of all, it's a shift with regards to generation. Now we're seeing solar and wind are conquering electricity supply. That has been true in the United States and around the world. And in particular, it's true in China. We'll take a look at China and what's happening there a little bit later. And then the other change is the use of that energy for electric vehicles, heat pumps, AI, and other things. Basically, all of these are electric uses as opposed to, in the case of fossil fuels, think about cars are burning petroleum to get motion. Unfortunately, they're very inefficient. They're only converting about 30% of the energy in the gasoline to useful motion, and the rest is wasted as heat. But with electric vehicles, it's 90%. So that's a huge shift to go into EVs and these other uses. And then the last thing is the connection. So you have all of this stuff linked together in electric grids, or you can be off the grid, and that's called decentralized power. But basically, everything that needs to be connected is connected to a source of power with battery backup. Then we talk about the efficiency advantage of the Electrotech system. And as I mentioned, the fossil fuel system basically wastes about two-thirds of the primary energy to heat. And if you want to put that in number terms, that's $4.6 trillion every year going up in smoke. And the bottom line is that Electrotech is 3 times more efficient because it bypasses thermal combustion. So we're eliminating thermal combustion and going directly from generation of electricity to use. When you think about it, this revolution is driven by manufacturing economics. And the best example of that is the fact that solar photovoltaics have dropped so dramatically since they first started to be used in large quantities about 2010. So in 2010, it costs about $100 per kilowatt to generate electricity with a solar panel. Today, it's 50 cents. So you've seen the cost of that being reduced essentially to 5%. And in this case, they're saying 99.6% since 1980. So that the costs have dropped dramatically, and therefore capital has shifted. And think about it, with the solar panel, you pay for the implementation of the technology, but there is zero fuel cost. If you buy a car, you have to buy the car and pay for fuel for the entire lifetime of the car. Likewise, with a natural gas powered generation plant. So that's the key difference, is that there's no fuel cost. And because of that, solar has moved from the smallest to the largest source of new electricity in 15 years. And it is the case that current manufacturing capacity is sufficient to meet very aggressive net zero pathways. So it's technically possible, but politics is a different matter, and we'll talk about that as well. I want to use this example. This is basically a box that is 15, let's see, what is that? 15, well, it is 21,000 square miles of solar panels, which is contained in this box, could provide the entire electrical needs of the United States. So think about that. That's a relatively small area. I'm not advocating that we, basically put a big solar array up west of Phoenix, but I am encouraging everybody to think about how that could be distributed across the entire country and power the entire country if we wanted to do that. Now, we're not going to do that right away, but it's possible. So now we talk about politics, and during the Biden administration, there were a number of very important pieces of legislation, which include the bipartisan infrastructure bill, the Inflation Reduction Act that affected energy, and then there were others that affected the implementation of manufacturing in the United States, especially the CHIPS Act. So with regards to solar and wind, there was a very important tax credit, 30%. That means that when you built a solar facility, you got a refund of 30% of your investment. And that was a major beneficial inducement for people to put in solar facilities, which is partly responsible for the amount of solar installation that you saw in that earlier table. With regards to transmission, there was a huge investment in facilitating transmission that helped open up the grid. With regards to manufacturing, made in America. So the CHIPS Act, we wanted to move the production of chips from China and Taiwan to the United States, and that is happening. And with regards to baseload power, there were incentives for nuclear and hydrogen. This has shifted very dramatically under the Trump administration. Instead of net zero being a focus and recognizing that there's a problem with climate, the Trump administration has basically taken the attitude that we don't have to worry about that. All we have to do is produce lots of oil and gas, and that's what their policy is based on. It's based on what they call energy dominance, so that we can provide the energy needed for AI leadership. With regards to coal and gas, there was going to be a phasing out via EPA regulations, basically making it more expensive to produce electricity from coal and gas. And that's been changed under the Trump administration. Under Biden, we had direct subsidies for renewables, and now we have basically a tariff-heavy approach. So the cheapest solar panels are made in China, but it's not cheap in the United States because of all the tariffs. However, China is selling those panels to the rest of the world. With regards to nuclear, we went from a policy to modernize those nuclear reactors to a very aggressive deregulation policy and a focus on small modular reactor mass production. So that is a process that's underway. The thing about that is that it takes time for it to occur. So the policy shifted last year, but it's going to take 5 years to see the results of that. And then with regards to grid management, the Trump administration has been dealing with tremendous increases in the cost of power that residential customers are feeling by shifting the burden of the cost of new power generation to the data centers that are requiring the power. And that's actually a really good thing. So one of the things I wanted to point out is that the Secretary of Energy, Chris Wright, spoke at Davos. And at Davos, he basically said the world needs to double oil production, and that's their strategy. And I just want to point out that that would be a catastrophic thing to do. You would be increasing greenhouse gases by 22 gigatons of CO2 per year. That's a 60% increase in energy-related emissions, and that would make it impossible to limit warming to anything that is going to be livable. So it's really a bad policy, and it's a sign that, at a certain measure, the Trump administration strategy is really wrong-headed. Okay, let's take a look at China. China has been going through an energy building boom, unlike anything the world has ever seen. You know that they're a considerably larger country than the US, maybe 3 times as large, but the scale of the energy construction in China is just staggering. They added 543 gigawatts of new capacity across all technologies last year. That's 12% more than all the power plants combined in India as of the end of 24. So in 1 year, they added everything that that India has ever built. And solar accounted for more than half of the new additions of generation capacity in China. They have massive facilities in Western China, and that are actually connected to the cities in Eastern China by huge transmission lines. And that if you look at the generation that China has added since 21, it's larger than the US system put together. They also have a tremendous competitive position with regards to almost all the industries related to green energy. So with regards to manufacturing, they produce 80% of the world's solar modules and 82% of the world's wind turbines. They may not sell those in the US, but they do sell them everywhere else. And there are vast areas of the world that everybody at one point thought, well, these countries will go from burning wood to burning coal to burning petroleum, and that's going to be the evolution of their energy system. And now what we're seeing is they're going from, a third world country to essentially a first world energy infrastructure using primarily solar. And that's a really, really good thing. So as you know, China has a very aggressive and state-supported system. It's also very authoritarian. And so I'm not advocating that we adopt a political system like China, but I think that we need to be impressed by what they're accomplishing and be focused on doing something within the United States as well. One other thing, and that is that China used to have a reputation of stealing everybody's technology. So if you shared with the Chinese your technologic ideas and blueprints and stuff, you'd find rapidly that they were producing it themselves. And when you came to claim patent infringement, they said, well, what you going to do about it? Because the courts in China will support us. However, in recent years, the Chinese have taken the lead in terms of developing new technology, and they hold 75% of global clean energy patent applications in 2025. So things are changing on that score as well. And then in terms of geopolitical influence, the solar modules that are produced in Southeast China are being found throughout Africa, Asia, Europe, Australia, every other place in the world. And the Chinese are also funding a lot of that stuff. They provide financial assistance. So they are extending their influence by virtue of the technology and the financing of global power production. If you look at if you look at the next 5 years of what's being forecast for power additions, these blue dots are the US. So we're looking at adding, 100 to 150 gigawatts per year. They're looking at adding 600 up to 850 gigawatts per year. And if you look at their total infrastructure, they're at 3.9 petawatts. And in the last 4 years, they've added 1.5 of those. And the entire U.S. energy production, electrical energy infrastructure is 1.4 petawatts. And this is where China was in 2025. They added that much compared to our entire infrastructure. And then look at the rest of the world. So China is taking a very aggressive approach. And guess what? That puts them in a position to do all kinds of other things, especially AI, because to the degree that AI is energy intensive, they've got the energy. Let's take a look now at the importance of storage. So in the old grid, we're talking about the 1980 grid. What you basically had is a static system of giant coal and nuclear power machines. These were large facilities generating power, and the grid was designed to be a one-way grid. It moved power from the producers to the users, and that's just the way it was. Well, in the 1990s, there was a wave of regulatory restructuring that allowed for independent power producers. These producers could set up power production facilities, and it doesn't matter what they are. They could be coal or gas or nuclear or solar or wind, but they can compete with the big power producers. And because at the time, combined cycle gas turbine plants were smaller, cheaper to build, and faster to permit than coal, that was the preferred technology that was implemented. And as a result of that, you saw that by 2016, natural gas officially overtook coal as the largest source of US electric generation. And by 2020, the grid had evolved to a multi-directional system. So you had independent power facilities putting power into the grid, or people using power and from the grid and then supplying their own power. And we also saw in the 2020s, and this is a result in part of the Biden administration policies and also technologic maturity, where solar panel costs and wind facility costs were coming down at the same time. So there was this massive growth that occurred within the United States at that time. And between 20 and 25, we see a huge increase in the amount of installed renewable sources. And then remember that these sources are intermittent. So at the same time, we also saw a very large increase in the addition of storage systems. So in 2020, there was 1.5 gigawatts of installed capacity of storage. By the end of 25, 5 years later, that figure had increased 27 times to 40 gigawatts. What does storage do? Basically, it shifts power from when it's generated to when it's used. It's an energy bank. And this is a chart that basically comes from a residential system. So in the middle of the night, there is no solar being generated. At 6 a.m., the sun comes up, you start to increase. In the middle of the day, you're generating maximum solar, and then it falls off. And when the sun goes down, the power stops. But you can basically, during the day, charge up your batteries. So this is the charging period, and then discharge the rest of the night and early morning hours such that your power supply is meeting all of the needs for the house. And I was in a house this last summer that's entirely powered by solar and batteries. It was built many years ago. The technology is fairly old for that house, but it's basically like this. And this is the same model that battery systems use even when they're scaled up to the grid level. They store power when there's an excess of power being generated and give it back when it's needed. All right, so let's talk about the AI revolution. This is going to be the biggest change in technology that we've ever experienced in the history of humanity. It's going to have a major impact on every aspect of our life. One of those is productivity. So it's becoming part of the economic infrastructure. And, I'm sure that everybody in the room today uses AI. I can't imagine that not being the case. And you all know what I'm talking about when I say that it's a force multiplier. If you need to do research, AI is a great way to do it. And it will also accelerate greatly scientific discovery. So right now, the big talk has been about large language models. And basically, what happens there is that the AI systems go and hoover up all kinds of information that's been accumulated really throughout the time of civilization, but mostly it's modern digital information. And then if you ask it a question, it can quickly research a lot of topics. But instead of large language models, think about putting large medical models or biologic models or chemistry models or whatever in the middle, and it would do the same thing. It would have access to a tremendous amount of information, and that accelerates the process of discovery and refining technology at a pace that humans cannot achieve alone. And I listened to a talk on a podcast recently where a guy was talking about medicine, and he said, think about a doctor that has to diagnose an illness, and he's familiar with 5,000 cases. That's his body of knowledge. And then compare that to an AI medical system for diagnosis that has access to 50 million records and can access them more efficiently than that doctor can access 5,000. That gives you an idea of the potential impact on the subject of diagnosis using AI. And the same is true for all kinds of other fields. The other thing about AI is that we're going to see it's integrated everywhere. And in particular, that's relevant to this discussion, it will be implemented and integrated into energy systems. And so that's going to be a huge topic going forward. And in fact, that's a very popular topic for discussion on places like LinkedIn right now. This is a graph that I just want you all to look at for just a minute and think about the rise of electricity, which basically early part of the 20th century, and it took 25 years to get to 40% penetration. And that's because they had to put in all those wires and everybody got hooked up and bought appliances and all that stuff. And then think about more recent technologies like the internet, cell phone, smartphone, and how quickly we've adapted those, but it's still taken a while. And then look at what's happening with artificial intelligence. Because the internet already provides the infrastructure for everyone to use AI, it doesn't require a big infrastructure, at least not for the communication part of it. And the adoption rate is tremendous. So we're seeing countries now that, are at 40 to 60% adoption rate. The US is not there yet, but this thing is happening very fast. And there's a comment that AI waits for no humans. So unlike the Industrial Revolution, the AI revolution is hitting every system simultaneously and rapidly, and that a lot of people believe that adaptability is going to be the most valuable human trait. And Friedman is famous for identifying that we're moving from a digital divide, so people are divided between those that are using computers and those that aren't, to a motivational divide, and that's the difference between those who are willing to learn at the speed of the machine and those who are not. So I wish everybody good luck in keeping up with the speed of the change of this technology. Now, along with all of the data centers, there's going to be a huge need for power. This graph identifies a period of time from 2014 to 2035, and it shows the demand for power by the different major grids that are in the United States. And what you can see is that we've gone from a relatively low level. So in 2014, the annualized US data center construction budget was 1.6 billion. As of July 25, it was 41 billion. That's $41 billion. And look where it's going to be in 2035. It's going to be about 105, $108 billion of investment. That investment is going to have an investment alongside it of power generation. And so now let's take a look at how the grid is set up. The way the grid is set up, and this is kind of a simplified view of things, but it's important to understand that power is generated typically in large stations. The generation occurs at 11,000 to 13,000 or 11 to 13 kilovolts, so 13,000 volts. It's then stepped up to 500,000 volts through a transformer for primary transmission. And then it may go through a secondary transmission where that stepping is also occurring. And then it's stepped down for distribution. All of this is three-phase power. So three-phase power basically implies that there are three phases that are laid over each other, and therefore there is no drop in the power. And three-phase power is critically important for industrial applications. But by the time it gets to homes, basically it's one-phase power, and it's at 60 cycles and 120 volts in the United States. In Europe, it's at a different voltage, but the point is, it starts out here, it's transmitted at very high voltages, It then gets distributed and ends up being very low voltage, 60 cycle AC power. This is the North American grid. There are 23 assessment zones here, a bunch of them in Canada and the United States. And this is a presentation put together by NERC, which oversees the technology of the system. And they're predicting that 13 of these zones are going to have elevated or high risk of brownouts or blackouts as we move forward. Those include ERCOT, the Northwest, the central part of the United States, and then the orange ones are slightly less risk. But it gives you an idea that North American grid is going to be stressed and more going forward. And a big part of that will be the data center demand. The other thing I want to look at right now is the relationship between using power as alternating current versus direct current. So those of you who are familiar with the story of the identification of electricity and the development of the initial energy infrastructure will remember that Thomas Edison originally was promoting the idea of direct current and in fact installed a direct current power system in the city of New York. And Nikola Tesla was basically advocating alternating current using spinning generators. And this battle was fought, but Tesla won. And the reason he won was because when you want to move power over long distances, alternating current is really a much better way to do it. So what is alternating current? Basically, because of the way that power is generated in a spinning generator, you basically have the power going through a full cycle every 1/60th of a second. And those 60 cycles or hertz are what we refer to as our power cycle standard. And it's real easy to step up alternating current to higher voltages, as we saw earlier. Whereas direct current, the electrons are flowing in a single steady direction. However, direct current is what all electronics use. So you can't put alternating current into electronics, you put direct current. So everything that you're using for your laptop, your cell phone, your EV batteries, and AI chips is all DC. And guess what? AI chips is what is at the center of the AI revolution. So you're going to have to go back and forth between AC and DC on the modern grid. How do we do that? Well, if we're going from AC to DC, we basically rectify. So you have a device that essentially converts that alternating current into a steady DC current. And if you want to go from DC to AC, basically you invert that current so that it is in that 60 cycles. Now, with nuclear power stations, with coal power plants, with natural gas power facilities, they're all generating power as AC and they're shipping it as AC. But if you're talking about solar power, it's generated as DC. Likewise with wind power. So it used to be that all the generators were AC, but now some of the generation is DC. So basically, you're going to have to go back and forth several times, or you can avoid that entirely by staying one or the other. And I do want to point out that high voltage DC is a technique or technology that's being used in China right now, and they're looking at ultra high voltage direct current that are at, I think it's 15,000 kilovolts, so substantially higher than what we're using. And they're able to transmit that power over 3,000 kilometers. Oh, yeah, this is plus or minus 1,100 kilovolts from Western China to Eastern China, and they lose only about 3%. So it's an amazing technology, and they have three of these very large long distance facilities. So if somebody tells you, well, it's impossible to put a solar farm in Arizona and move that power to Missouri, you can tell them, no, it's not impossible. There's a technology to do that. All right, so now let's take a look at federal and state regulation. The important thing to recognize here is that there is regulation that occurs at the federal level through the FERC, and that there's regulation that occurs at the state level through public utility commissions, and they have different responsibilities. So the FERC is responsible for interstate transmission of electricity, wholesale electrical sales, transmission rates and tariffs, reliability standards, but the state is responsible for retail electric rates, distribution systems, service quality, and resource planning. Utilities are often vertically integrated, so they have generation, transmission, and distribution infrastructure as part of one utility. So again, here we've got all of these assets. They serve retail customers. They're regulated by the state PUCs, and they recover costs through regulated rates. In those cases, the rate structures are basically designed to deliver power at a consistent price. So your electric rate doesn't change. But in other systems, it can change, and that creates a much more interesting environment to produce, transmit, distribute, and use electricity. And we'll take a look at that. Transmission owners, so basically you have independent system operators and regional transmission organizations. Owners is not entirely correct because in many cases they don't own the assets, but they do manage the grid. They ensure reliability and they maintain the wholesale electrical markets. The distribution utilities do own and operate their distribution systems, and they do all the metering, the billing. And when your power line goes down, those are the guys that show up with a truck to fix it. One of the concepts that's coming to the fore right now and is going to be very important, I think, going forward, and we'll discuss a version of that, is the data center microgrid. So the idea is that you can have a variety of sources of power. In this case, we've got solar and wind. And then we also have a means to store that power. So this is all for the accumulation and delivery of capacity. And then you have the data center itself, and it may have, some other local sources, but basically you can deliver all these sources here and you can stay in DC. So if you're generating power in DC through either a solar panel or a wind turbine and storing it in a battery system, and all of these electronic devices in the data center are using DC, you never have to go to AC, and that avoids any conversion losses. Okay, back to the ISOs and RTOs. Again, the reason I put this slide in is just to make sure that we understand that this is the organization that we're going to be looking at in a moment, which is ERCOT, which is the grid manager in Texas. And they're responsible for balancing supply and demand, economic dispatch, congestion management, wholesale market design and settlement, which is hugely important because that's where economics come into play. They also do long-term transmission planning and interconnection of new generation and storage. Do want to add that there's one other entity that we mentioned earlier, and that is the North American Electric Reliability Corporation, and they develop and enforce reliability standards for transmission operators, generation owners, and balancing activities. Okay, so now let's take a look at ERCOT. ERCOT is an independent system operator. They are a nonprofit corporation. They're governed by a board of directors and subject to oversight by the PUC of Texas and the Texas legislature. And their members are consumers, cooperatives, generators, power marketers, retail electric providers, basically everybody that's on the grid that's either supplying power or using power is a member of ERCOT. And that enables them to manage the flow of electric power to 27 million customers, which is 90% of the state's load. They have 54,000 miles of transmission lines. They encompass 1,250 generation units, and they perform financial settlement for that bulk power market. And in Texas, you can opt to have a fixed power price, or you can go on the unregulated power market. And if you do that, there's some tricks that you can play to make sure that you get the lowest cost of electricity. So this is ERCOT and the role that it plays. And this is a great example of how ERCOT works. And actually, this is the title of the talk. So for those of you who may have nodded off, if you just pay attention to this slide, then you'll come away with something useful. This shows you all the layers of power generation that go into delivering the consumer demand, which is the top line here. That is how much electricity is used at any given time. And you can see that during the day, it varies from 40,000 megawatts up to 50,000 megawatts. But within that, it's composed of very different mixes at different times of day. So at the bottom of this, essentially this pyramid, is the nuclear power generation, which is basically the same amount of power for 4,000 megawatts of power is generated 24/7 by the nuclear power plants. With regards to coal, it fluctuates a little bit. So it goes up in the morning, very early morning hours here. Then it's fairly low during the day. And then in the evening, it goes up a little bit more, but it's fairly stable throughout the day. Natural gas power generation fluctuates quite a bit. So you can see that initially it's at a fairly good level. It peaks out here right before dawn. And then all of this wind and solars, mostly the solar's kicking in. So it drops down to absorb the difference, and then it picks up again in the evening. Now you see wind is strongest at night. So there's wind at night, and solar kicks in the middle of the day. And in the middle of the day, solar is over 50% of the energy mix in Texas. So this system essentially accommodates all these different sources, accommodates the fact that solar is only working during the day, but during the period that it's working, it's a huge source, and that wind seems to be strongest at night, and that you've got natural gas power generation to come to make up the difference. And then the other interesting thing is this little shoulder here. So as you go into the evening and the solar incidence is lowering, you're increasing the natural gas energy power production and adding back all the electricity that was stored by the batteries during the middle part of the day to give you the power that you need in the evening. And that's the whole mix there. It's a great example of how all these different baseload and intermittent and hydrocarbon and renewable and other power sources, plus the battery storage, coexist and provide the power that people need. So now let's move on to the perspective of the data center developer. The data center developer has been hired or are the AI company themselves. So you've got Amazon and Microsoft and a bunch of other companies that are going to build out all of this capacity of data centers. And they face a series of challenges. One of those is that traditionally, when they needed more power, they just went to the utility and said, I need another 100 megawatts of power. I'll have my facility ready in 24 months. Can you give me a connection at that time? And in the past, it was easier for the big utilities to do that. But now, with all of this demand for power coming at once, there's an interconnection queue, and you may have to wait in line 5 to 7 years to get that power instead of, the time to build your facility is only a year and a half to 2 years. So that's a problem. And the other problem is that these queues are clogged with speculative requests. So somebody might say, oh, I'm going to need 100 megawatts in 2028, but they're just putting a request in and it's not necessarily going to materialize. So with all that, you've got this problem of the bottleneck. The second problem is the power density. So in the case of the AI chips, and think specifically of the NVIDIA chips, they are much more power hungry than the traditional microchips that were used for data centers. So a rack density is a measure of how many kilowatts one rack takes. The traditional data centers used rack densities of 5 to 15 kilowatts. AI native facilities in 2026 that are at 30 to over 100 kilowatts per rack. So if you go from 5 to 100, that's a 20-fold increase in the energy density. And what that means is that these data centers require a much higher level of power, and typically the substations and distribution lines that are in existence were not built to deliver that kind of concentrated power. So there's an incremental cost to add in additional transmission and distribution capacity. And then the other issue that they're facing is that these very high density chips require cooling, a lot of cooling, and that creates another demand for energy. The second set of challenges has to do with the fact that many of these guys are required to meet certain net zero commitments, but AI requires very consistent baseload power, and intermittency of solar and wind means that they're going to have to secure massive amounts of battery energy storage so that they can spread that generation that might occur over 6 to 10 to 15 hours over the entire time that they need power. The other issue is that solar farms take a certain amount of land, and in many parts of the country, and I'll give examples that in Virginia, I think has one of the highest densities of data centers. There's not a lot of land that's available to set up a solar collection facility. And another place that's the same way is Silicon Valley. They both want to do it, but they don't have a lot of land to do that with. Then a fourth category of issues is that as all this power demand comes on, there's a risk that that power demand is going to cause brownouts or blackouts, and that makes regulators nervous. It also makes consumers nervous. You know, imagine that the power goes down and the first thing you say, oh, it's that damn data center down the road is sucking all the power, right? So one of the things that's happened in Texas is that the regulators there have introduced laws that give the grid operators the authority to forcibly disconnect data centers during emergencies. And they can do that without warning. So if you are a customer on the grid and you've got a data center, they can shut your power down without telling you, which means that you really need to be conscious of having reliability, like battery storage or backup generators, or generate your own power so that you're not faced with a loss of data and credibility with your customers if your power center gets shut down. And then the last thing that I mentioned earlier was that there's a concern, and for example, in the PJM grid, power prices have essentially doubled for many of the residential customers in the last couple of years, and it's caused by this data center thing. And so the Trump administration is currently trying to make sure that when people want to build new data centers and they're going to want to get electricity to do that, that they are paying for the incremental cost of that generation capacity. Now let's look at one of the solutions that data centers have, which is the behind the meter architecture. And this is very much like the earlier slide on microgrids. So basically, in a traditional setup, the power is flowing from the grid through the utility meter to the data center. In behind the meter setups, the generation sources, whether they be gas turbines, small modular reactors, or solar, and the storage, are connected to the data center behind the meter. And if you look at what's happening today, and I'll show you an example of this, large-scale AI campuses are increasingly using a combination of modular natural gas turbines and solar and partnering with nuclear plants to provide the baseload power that they need, and that the battery systems are the glue that pulls this all together, just like the example that we saw of the ERCOT grid. They provide a lot of benefits to those microgrids effectively. This is just an example of one. So you've got a couple of different Sources, this is a aeroderivative gas turbine. There's a company that's producing a supersonic aircraft, and they were building their own engines. And since their aircraft is not ready for production, they're selling those jet engines to generate power. Or you can use a combined or single cycle gas turbine. Here's solar power, and then here's the battery storage. So the advantage of behind the meter co-location is one that you can get to market fast. And one of the problems right now that people are facing is that it takes a long time to get one of these gas-powered uh, electrical generation systems. So if you get a hold of them, you can build your facility fairly quickly versus having to wait for the grid to ramp up to meet your needs that could take 5 years or 7 years. Another thing is that if you generate your own power, you don't have to pay demand charges or transmission or distribution fees, and those can make up 30 to 50% of a traditional utility bill. The other thing that you can do if you are purchasing power from the grid and you have behind the meter generation and you have storage, you can play a game in Texas where if you know that the grid rates are going to go up in the evening, and typically they double in the evening, you can basically shut down your grid access, turn on the battery, and avoid those high cost periods. That's called peak shaving. The other thing you can do is when your workloads are low, you can sell that power that you're generating back into the grid and turn that power generation capacity into another revenue stream. And the last point here is that it provides you physical security. So if the grid starts going down, since you're not connected, or since you have some insulation from the grid, you can avoid that brownout or blackout. But there are some challenges to going off grid. It's not a silver bullet. One thing is if you put in a natural gas powered facility, you've got to bring that natural gas in. And, natural gas, there are logistics issues there as well. There's also regulatory friction. So utilities may not really like the idea that you're jumping off their load, but you want to access their power grid when you want to. So they may have some kind of fee related to that arrangement. And then if you have a hydrocarbon powered generation facility, you also have to obtain the air quality permits. So one of the thresholds that people need to go through is getting that air quality permit. So here's a case study of an absolutely massive behind the grid power facility that's being built in West Texas. It's in Pecos County, West Texas, which is just south of Midland and basically on the edge of the Permian Basin. It's called the GW Ranch Project. It's developed by a company called Pacifico Energy, and it's the poster child for the private grid movement. It's designed to bypass the traditional utility connection queue and that multi-year bottleneck. It's the largest permitted power for AI project in the entire United States, and it's designed to operate entirely behind the meter. There's no physical connection to ERCOT. Why West Texas? Well, one good reason is that you're next to this basin, the Permian Basin, that is primarily an oil basin, but a lot of that oil produces natural gas at the same time. So there's what's called associated gas that's being produced. And since there's not a lot of pipelines in West Texas to move that gas to market, a lot of it is stranded. And therefore, that gas is cheap and it's going to be around for a long time. So you're proximate to the fuel if you're using natural gas. And then in the case of solar, it's got very high solar insolation, which is the intensity of the sunlight. And Texas is an environment, a business environment, where things generally move pretty quickly. And so in early 2026, the Texas Commission on Environmental Quality issued the air permits that were needed for that GW Ranch project in record time. Here's the actual facility. This is 7.65 gigawatts of gas-fired generation. And to give you an idea, a gigawatt can typically power 700,000 homes. So 7.65 gigawatts is a huge number of homes that it could power. In this case, it's all going to be AI machines. And of course, it's tapping into that stranded gas. And then they also have a solar component, which is about a tenth of what the natural gas is. And that's working during the day. And then they have a 2 gigawatt hour battery energy storage system so that they can store up that solar and then release it at night and get 24 by 7 renewable power. So this is the poster child right now. It's an immense facility. I imagine there'll be more. They probably won't be in Virginia or Silicon Valley. They're probably going to be in places like West Texas. So that brings us to the end of the presentation. And I want you to just retain a few points from this. First of all, there's no question that the ability to use energy has had a massive impact on the quality of life of humanity. All of that came originally from coal, oil, and natural gas. And all of those power sources rely either on heat to provide useful heat, or they rely on, in the case of coal, the big revolution was steam. So you're going through a phase change from water to steam, and there's this tremendous expansion that occurs with that. Likewise, when you combust oil, for example, diesel or gasoline, there's an expansion of the combustion gases. And that's what's driven all of the machinery, the cars and the tractors and the trains and the airplanes that we use today for transportation. So we've gotten a great quality of life. But there's greenhouse gases that we need to be aware of and global warming that we need to protect ourselves against. And that poses a danger to humanity. And then when you look at the US energy system, we realize that it's historically been based on fossil fuels, but that we're going through an energy transition at this time from fossil fuels to renewables. That gives us hope for the future. The question is, how quickly can we achieve that? And when you look at China, they've shown that you can implement a lot of solar very quickly. They put in, I think they put in as much solar last year as we have in total. I mean, it's just a phenomenal number. And yes, they have a lot of coal burning, but the prediction is that China will stop increasing the amount of coal it uses and basically be shifting towards renewables over the next 20 years. We also see the rise of the battery storage systems. These shift power delivery in time to meet demand. And there's not only batteries, but there's all kinds of other systems. There are mechanical systems that, for example, you can pump water up a hill, store it in a reservoir, and then put it down through a generator when you need it. In Finland, they have these systems that rely on large tanks that hold sand, and that sand is heated up to 500 degrees centigrade during the summer, and then they use basically technology to extract that energy and turn it into electricity or turn it into heat in a local heating grid for the people that live in a town. We're looking at the AI revolution. It's very consequential and will produce a lot of power demand. And we're forecasting a huge demand. We're just seeing the very front end of that demand thing kick in. It's going to have a lot of impact on the grid. The grid is a very complex system. Some say it's the most complex system that man has ever created, and it works well, but it can get stressed, and we can expect that it will be stressed. ERCOT is an example of I think, a very proactive grid. And as we saw in the example today, they have mastered the art of mixing stable sources like coal and nuclear with fluctuating sources like natural gas, and then the renewables of wind and solar and the augmentation of batteries. With regards to data center developers, they've got lots of challenges, but they've also got lots of money. So I have a feeling they're going to solve their challenges. And as they do that, they got to keep in mind that it's hard to get land and power for data centers. And one of the solutions that they will be looking at to a great degree is these behind the meter facilities. It's the fastest way to build and connect. It's happening today. It's happening all across the country. And I hope for the students that are part of this class that that's going to be part of your future. And with that, I thank you for your time and attention. Happy to answer any questions.
Oh, wonderful. Great talk. It covers a lot of territory. So, as is our custom here, we want to have the students ask the first set of questions. So, if you want, you can take your unshare, Jack,
Yep.
so we can see everybody. Yeah.
Okay.
Okay, great. Students, come up with your questions. Please introduce yourself, and more importantly, unmute yourself before you ask this question. So go ahead.
We have a question. Hi, my name is Adam. I'm in the Energy Systems Engineering program at Lehigh. First, I wanted to say thank you for presenting. I really enjoyed it. I have a few questions. So first, I wanted to ask about the case study you mentioned, or at the GW Ranch data center. I wanted to ask about the battery. Specifically, do you know like what sort of technology it uses, or is it like a conventional like lithium ion sort of thing?
Great question, Adam, and thank you for that. So what I understand right now is that they typically use LFP batteries. These are
Lithium iron phosphate.
yeah, lithium iron phosphate batteries. And the reason those batteries are used is that they're not as prone to combust spontaneously. And and of course that's been a problem in this revolution, whether you're driving an electric car or using batteries for anything else. Many of the early batteries were prone to have a runaway thermal reaction where they would explode. I personally have a hobby of flying radio control model airplanes, and most of my planes, in fact, all of them are now powered by batteries. So I have extensive experience with lithium ion batteries, and I've had a couple instances where they have exploded on me.
Hmm.
They produce a very hot fire that is, if you have a bus or a car powered by batteries, can be quite catastrophic. So I think the different chemistry, the lithium LFP batteries are less prone to explosion. There's a new technology that's coming to the fore, which uses sodium ion batteries, and they do not explode at all. They don't have the ability to charge or discharge as quickly as LFP batteries do, but I think that that can be improved and that they are going to be less costly than LFP batteries when produced in volume. There's another technology called vanadium flow, and that technology is even slower in terms of its ability to absorb power and discharge, but it would be perfect for longer term applications, and it's less costly per unit of storage. And then there are the mechanical systems, which I alluded to. So one of those systems, which is produced by a Swiss firm, basically has a large structure. And what it does is it picks up cement blocks and elevates them, let's say 6 stories, and then stores them in this structure. And that's how you accumulate the power. And then to discharge the power, you basically do the reverse. You lower all these concrete blocks to the ground. I don't know what the overall efficiency of that is. I believe most of the battery systems are in the range of 85 to 90% round trip efficiency.
Mhm.
Then the other alternative that people have implemented actually are these pump storage facilities. And that involves pumping water up into a tank above ground or up a hill into a reservoir and then cascading the water down and using it to run a turbine to produce electricity. So, and then I did talk a little bit about the thermal method that the finished people are using. So I think that there's going to be a lot of innovation in the field of energy storage, and that as time goes forward, we're going to have an array of choices, and that people will make choices based on economics, based on how quickly they might need the power. So if they need the power really quickly, you could actually go to a capacitor, a large capacitor that you can charge up and discharge very quickly. Next choice would be some kind of battery system like the lithium batteries. And then for longer term, you might have a mechanical storage system. So I think that the guys that are currently taking this course, you're going to have a nice menu of choices, and you'll be responsible for not only selecting what's the right system, but implementing them and maintaining them. And therefore, storage technology is going to be an important part of your portfolio.
Thank
Okay.
you.
All right. Questions from students. Please unmute yourself, introduce yourself. Students.
Hi, Jack. I also have a question on batteries. My name is Selena. I'm also part of the ESE program. Um, from my understanding, batteries haven't really grown much because they have challenges of cost and efficiency. In your perspective, what do you think the biggest challenges are in that industry?
Oh, well, I think that one slide showed that from 20 to 25, there was a 40, what was it? A huge increase in battery storage.
Oh.
27-fold, I think it was the number. I think that's going to continue on a global basis. But you're right in saying that people will have more choices as to what technology that they can implement. So, for example, recently I've heard from people that are looking at doing production of sodium-ion batteries, and they take a greater volume than um, the lithium batteries do, but it may not matter for a lot of applications. If you're looking at a ground-based energy storage facility, that volume and that weight of the batteries may not make a difference. Whereas if you're looking at using battery storage to power an airplane or a car or a train or something like that, it would. So I think in general, there's going to be a lot of choices. There's a company called, I think it's Donut, and they are going from batteries that have electrolyte to batteries that are solid state. They claim that these batteries can store more energy per unit. They can discharge just as quickly, and that they last considerably longer than the current battery chemistry. So one of the things about the lithium batteries that I note is that, after a couple of years of use, they just don't charge up and discharge as well. So I think part of the trick will be something that lasts, instead of 3 years or 5 years or 10 years, lasts 10 or 15 or 20 years. And that'll be a big thing. I do think if you want to achieve that probably batteries aren't the answer, that it's probably going to be mechanical storage of some sort. And for example, one of the storage technologies that I'm aware of basically takes a flywheel and it ramps it up to a speed of like Mach 2. I mean, it's just an incredible speed that this flywheel is spinning inside a vacuum. And you have a mechanical impetus to get the flywheel spinning, and then you can do the reverse, just like electric cars can use the braking system to repower the battery. And so I just feel like there's going to be many choices, and the economics will evolve. And so, we'll just have to check in every year and see what's available and what the specs are. And then you'll have to make a decision based on what you need that power for, what's the best choice. Which is actually kind of a cool thing that the state of technology is constantly changing. And, there's things that are established technologies, that there are things that are new technologies, and there are things that are technologies to come. And all of those will be relevant, and that'll make your job very interesting.
Hmm. Thank you.
Yeah.
Right. Questions from students?
Hi,
Meanwhile, if you have others, can you put your questions in the chat box so that we can go through all of them? Yes. Who has a question?
it's me. Hi, Jack. My name is Bintusila, and I'm also part of the ESE program. I have a question regarding the model of bringing their own generation for AI data centers. Is there any study that have proven it to be techno-economically feasible? I mean, I know mining company do that. They have their own generation because they're in the middle of nowhere and they avoid the transmission fees. But for them, is it techno-economically feasible? Sorry, because it's a full-time job to ensure safe and reliable power services. Or are they willing to use AI to make this happen and then create a parasitic load?
All right. So let's break that down into a couple of parts. First of all, there are plenty of options in terms of generating power, and they range from, converting hydrocarbons into electricity, either through combustion type of technology or a fuel cell type of technology. So, for example, there's a company called Bloom that uses natural gas to generate electricity with a fuel cell. There are, of course, solar cells, which are incredibly cheap now. And, just think about a 400-watt panel costs about 150 bucks. If you were to run that panel for 25 years, and there's nothing that says you can't, because they do degrade, but not that much, you would generate 21 megawatts of power during those 25 years for no fuel cost. So that's an interesting alternative. There's wind. There's geothermal power, which is using the difference between temperature gradients under the earth and at the surface. Um, there's going to be small modular reactors, and that technology I think is going to take 5 or 10 years to come to the fore. But at that point, the whole idea there is to automate the manufacture of the reactor. So think about the big power plants that were built that were nuclear in the past. If you've ever visited one, they're immense facilities, and they take 10 years to build and 10 years to permit, and it's just ridiculous how long it takes. But the small modular reactor, the idea is we're going to build those in a factory. It'll take 2 months to build it, then you ship it, set it up, turn it on, and you've got power. Now, you would still have a permitting equation that you need to take place, but if you permit the design, then that handles a lot of the delay that would occur from the Nuclear Regulatory Commission. And therefore, what you need to permit is not so much the design of the reactor, but the local permitting requirements. So those would be like state and local requirements. So there's going to be a lot of choices in terms of generating and storing power. And I think that we will see that the idea of distributing power becomes incredibly relevant as we move forward in time, such that people like yourself will be asked to provide power at a certain location within a certain period of time, and you'll have lots of choices for getting there. As far as the economics, the economics are changing all the time, but I think that many of the alternatives, it'll be the case that it's as cheap to produce your own power as it is to buy power from the utility. And that is like the most critical thing. And of course, as you talked about in the case of mining facilities that are remote, you have no alternative. You've got to produce your own power. So, it used to be when you had a facility like that, there was one choice, a diesel generator. You'd bring in the generator, bring in the fuel, and produce your own power. That was it. But today there's lots of choices, and there's some that are very attractive.
All right. Questions from students? If not, I'm going to switch to
Hi,
the chat.
Jack. Hello.
Hello.
Yes.
Hi, my name is Yunus Kadzema. I'm also an ESE student. I was just wondering from your perspective, I was reading up on ERCOT and I see one of the things that they've decided to do is the bench zero plan. that they plan to just group large interconnection queues into these batch projects. But I was wondering, what are the downsides of doing that if they've started? Are there any case studies that it actually works? Because from my perspective, it seems like it favors big tech hyperscalers rather than small innovators.
Well, yeah, there's definitely an advantage to being big and having lots of cash, right? So, but when you're small, you can be nimble, you can be innovative, and come up with solutions that might not make sense for a larger company that has a lot of money. Uh, and that's, listen, the shift that's going on right now with AI is primarily being driven by larger companies, but the business that results from that will be shared by many, many companies, I think. I don't know if that answers your question, but those are some thoughts that come to my head.
Okay. So here's a question in the chat box, Jack. Uh, are most AI data centers that bring their own generation, do they use multiple generation sources, or do they stick to uh, gas turbines solely?
Okay, well, great question, because one of the issues that people have to face right now is that if you just go into the market today to buy a gas turbine, it's going to take 5 to 7 years to get that delivered because there's such a backlog on these things.
Mhm.
Now, that's being changed by the fact that there's an international cadre of manufacturers, but those manufacturers, if you bring that equipment in, you'll be subject to tariffs under the current regime, and that could affect your economics significantly. So I think that the power generation options, there are going to be things like solar and gas. Um, they might even put in a diesel-fired generation facility while they're waiting for something else to be built. But it's going to get difficult. And I think one of the primary reasons for that difficulty is getting a hold of these gas-fired generation turbines. Everything is all locked up right now. So if you don't have something locked up, you don't have many options. And the thing about solar is the power density is not nearly as great as nuclear or gas. I mean, it takes a big field of solar collectors to generate the same amount of power. And you may not have the ability to get a hold of a large plot of land to do that. So I think that's going to be the great complication, is that the big power generators, it takes a long time to bring something online, but it's caused people to be creative. For example, and I think you were talking about this, Rudy, Microsoft has gone to the 3 Mile Island facility, and they're revitalizing one of the nuclear reactors that was shut down when the incident occurred, that was what, 1979 or 8?
79, yeah.
79. Yeah. And so it's causing people to think in very creative ways about what are the options for solving this problem.
Yeah.
Now, let me just make a comment on nuclear. I think the advent of small modular reactors is probably a very positive thing, because when you think about having the ability to generate 100 megawatts, in the size of a shipping container, and I don't know if that's exactly the right number, but let's say that it is, that could be pretty attractive. But there's going to be a lead time on that too, because they've got to get the technology developed. The NRC is going to have to be involved. They need to approve the design. They need to approve the actual manufacturer before that facility can be moved to a generation location. And then the other thing that's on the horizon right now is fusion. And I remember when I was a high school student going down to visit the Los Alamos laboratory facility, uh, and meeting with some of the physicists that were working on fusion at that time. And that was a long, long time ago. That was 1975. And these guys at the time would say, fusion is not quite ready for deployment, but it'll probably be ready in 20 years. So 20 years would have been 1995, didn't happen. We're actually 30 years beyond that point, and it still hasn't happened. But if fusion ever happens, it could be pretty fantastic in terms of adding a lot of power to the grid. So that's another possibility.
And in fact, related to this particular question about nuclear resources, there was a question in the chat box about what about waste fuel?
Yeah, that's a great question because as we use nuclear fuel for in a standard fission reaction, you produce waste products and they're collected, but they're still radioactive. And in fact, there's a nuclear design concept called a breeder reactor that basically creates plutonium out of the original fuel, and then that plutonium is used to power plutonium reactors. But of course, as you all know, plutonium is both a way to make nuclear bombs and also a very dangerous radioactive material with a half-life of something like 45,000 years. So one thing you would not want to have is an accident that involved dispersal of plutonium. These are all issues that need to be considered. And you're right to say, Rudy, that we really need to pay attention to this issue of nuclear waste management. If we're going to incorporate more nuclear going forward, whether it's large reactors or these small modular reactors, we still have to solve the problem that everybody's put to the side, and that is, what do you do with the waste? Because it remains radioactive, for some of it at least, for tens of thousands of years. So you're making a decision today that's going to affect people that might be alive 20,000 years from now.
And so there's a question in the chat box, and I'd make this the last question. Um, Availability of government incentives that will encourage AI data centers to utilize renewable energy to generate electricity and store excess with BESS would prevent main grid erratic withdrawal of electricity without notice. Well, I think this question is about and incentivizing, clean energy to be the behind the meter resource.
Right.
I'm not sure there's a question there. I apologize. Yeah.
Well, yeah. So let me make a comment on what the system was under the Biden administration. So the Biden administration implemented under the Inflation Reduction Act these tax credits, and they started out at 6%, and you could actually quickly get up to 30%, and could even get as much as 40 or 50% as a tax credit, depending on meeting a certain set of qualifications, and they included things like using domestically produced materials, abiding by local wage and work requirements, just a whole series of requirements that encourage things that we generally want. And they were a powerful incentive. For quite a while, there was a whole market that was set up to monetize tax credits that were associated with these solar and wind facilities. And that's a big reason that the industry took off. And the Trump administration came in and said, we're just going to eliminate those. So the solar, utility scale solar, basically to qualify now, you have to start construction of a facility by July of this year, and you have to finish it by December of 2027. That's a fairly narrow window. And I do think that we'll see that the deployment of solar is negatively affected by this change in policy. And frankly, I think it's a dumb move. I think that that policy should have been left in place. But and I would point out that oil and gas, while it doesn't have the same tax credit, it has plenty of tax benefits, such that many people, when they invest $1 in the development of oil and gas, they're getting a current year write-off of anywhere from 60 to 80 cents of that dollar. So they're investing really only 20 to 40 cents to
Hmm.
drill that well. And I would just say it's just bad policy on the part of the Trump administration. It's unfortunate, but the countervailing force is that the policy was effective in reducing the cost of solar panels. As we saw, the panels went from $100 per watt down to 50 cents a watt. And they're so cheap now that there's nothing else that can compete. If you look at a levelized cost of energy, solar is the cheapest, wind is the second cheapest, and the gas plants are the third cheapest. But they imply a lifetime of fuel purchasing. And, natural gas prices right now, they're about $3 an MMBTU, but what would happen if they were $10? You'd probably regret that you built a natural gas powered generation facility. So you have to take into account the risk of building a hydrocarbon powered facility when you don't know what the future price of the hydrocarbon is going to be.
Thanks a lot, Jack. Any last question for Jack? We're already in overtime right now. So if there's one last question, it was a very comprehensive talk. I think you covered a lot of different bases. In fact, anybody? Okay, I'll thank you again, Jack.
Thank you,
And just
everybody.
so next week, I believe, or sorry, 2 weeks from now, we'll have a gentleman from NERC. We'll be talking. NERC stands is the body that implements all the mandates that come from FERC. It's Federal Reliability Council. So that talk will be 2 weeks from now, and so it'll be the same time, 12 noon. Thanks a lot, Jack, and I really appreciate your patience. You get stuck with us beyond a lot of time, so thank you again.
Thank you.
See you all in 2 weeks.
Have a nice day.
Thank you.